An example data set run on the SR7500 DC is shown here. This data is from a 200 Dalton inhibitor, 4-carboxybenzene sulfonamide, binding to carbonic anhydrase 2. This example demonstrates the extremely low noise characteristic of the SR7500 DC instrument and shows that it can measure small molecule binding with great confidence. The image to the right of this slide shows the placement of the sensor chip on the instrument prism. Sensor chips are available with a wide variety of surface coatings, including the industry standard carboxymethyldextran and planar chips with carboxyl groups in a polyethylene glycol background. The flow cell with a separate path for each channel is then positioned and locked over the sensor chip surface. The flow cell is readily accessible and is easily taken apart and cleaned in case of a clog. The small volume and low dead volume flow cell in combination with high flow rates lend itself to the measurement of very fast kinetics. The accessibility of the flow cell also opens up new avenues for investigation through a specialized collection of flow cells that can combine SPR measurements with other analytical techniques. These flow cells create the opportunity to couple SPR with electrochemistry, multi-mass spectrometry, and fluorescence or light-activated binding events. The pump, injector, and SPR instrument flow cell are connected in series with PEEK or Teflon HPLC fluidics. You can minimize the system volumes by using very small 64 micron inner diameter tubing, or you can use much larger inner diameter tubing to inject samples containing particulates, such as cell lysates or whole cells. The sample loops can be changed to accommodate very short, low volume injections or long injection times, even at 50 microliter per minute flow rates. The fluidics are easily and inexpensively replaced in the event of a clog or contamination. Our two most popular sensor chips are the planar carboxyl chip and a chip with a three-dimensional carboxymethyldextran surface. The planar carboxyl chip was developed by George Whiteside's group at Harvard University. It is a low-capacity chip, which creates good kinetic data. This chip works great for 1,000 to 1,200 Dalton peptide analytes, as well as for large to very large biomolecules. It has very low non-specific binding characteristics due to the polyethylene glycol surface coating. The carboxymethyldextran chip has been used in the vast majority of published SPR studies. It is a flexible, protective hydrophilic matrix with large immobilization capacity and works great for small molecule analysis as well as for peptides and proteins. The surface also tends to resist non-specific binding. We also have available a number of pre-derivatized chips, including streptavidin or nutriavidin, nickel NTA, as well as a planar hydrophobic surface used for lipid work. Experiments are easy to set up and run using Reichert's AutoLink software. This fully integrated software runs and continuously monitors each of the system components, as well as providing electronic records and detailed reports of each event in an experiment. This slide shows a typical run setup. A run table is constructed by dragging and dropping injection and dissociation methods, as well as pump commands, weights, temperature changes, and sample loop washes. The steps in a run table may be minimized using loop methods, where a vial number is automatically incremented each step through the loop. An editor allows quick changes to the injection vial positions when using AutoLink loop commands. This is Reichert's SPR AutoLink data acquisition window. This screenshot presents the left and right channels displayed in a 20-minute time window. Alternatively, the left minus right or reference trace can also be displayed. All scales can be auto-scaled or fixed manually using the zoom function. This window also shows the status of each of the system components. The time and response normalized injections from an experiment are imported directly into Scrubber, the data analysis application. Alternatively, text format data can be used in programs such as Origin or Excel. In Scrubber, the data can be critically zeroed relative to the X and Y axis, precisely aligned with respect to injection start time, cropped, reference, buffer blink corrected, and for most small molecule work, DMSO corrected. If the data for each injection has reached the equilibrium response, it can be fit to a Langmuir binding isotherm as well. The window on the slide shows a kinetic data fit where a model shown in red is fit to the actual data by floating the model equations, the rate constants, K on, K off, and the maximum response, or Rmax. In this case, the data is fit globally, providing a rigorous determination of important binding constants. Reichert's concentration analysis application is used to construct a calibration curve of time response or report points in concentration. The report time point is chosen based on how good the data can be fit with a straight line, quadratic, or third-order polynomial equation. This software application also calculates and plots unknowns and controls. Now we will transition to some data examples acquired on our SR7500 DC instrument. This first example is an antigen-antibody interaction using a capture approach. The idea of using a capture agent is to provide non-random mobilization of the ligand of interest, in this case the antibody. In this assay, GOAT anti-mouse IgG-Fc is first amine coupled to the sensor chip surface. This provides a covalent amide bond between a carboxyl on the chip surface and an amine on the antibody. Following the immobilization of the ligand of interest, mouse anti-human serum albumin IgG is injected over the surface. Finally, the analyte of interest, human serum albumin, is injected to determine its binding kinetics and affinity to anti-HSA. This slide shows a graph of the first step of the capture assay, the amine coupling of anti-mouse Fc. Initially, the carboxyl groups on the sensor chip surface are converted to NHS esters by injecting a solution containing 40 milligrams per milliliter of EDC and 10 milligrams per milliliter of NHS over the center chip for 7 minutes. The anti-Fc antibody is then injected and subsequently immobilized to the sensor chip surface via a covalent amide bond. The process terminates with an injection of 1 molar ethanolamine pH 8.5 for 8 minutes to deactivate any unreactive NHS esters. Once the anti-Fc antibody is immobilized, anti-HSA is injected and subsequently captured at the Fc portion by the anti-mouse IgG-Fc. Next, HSA is injected to monitor its binding to the oriented antibody. The process is repeated several times by regenerating the surface with 10 millimolar glycine pH 2 for analyzing a set of HSA concentrations. This graph presents normalized, aligned, and reference-subtracted time-dependent response curves for 5 different HSA concentrations, ranging from 20 to 1.25 nanomolar. The red line is a fit to a simple bimolecular model. As seen from the data, the assay fits extremely well to a 1-to-1 model with an affinity constant of about 4.4 nanomolar. Our second example demonstrates the binding of 4-carboxybenzene sulfonamide, a 200 Dalton small molecule, to immobilized carbonic anhydrase 2. Carbonic anhydrase 2 was amine coupled to a carboxymethyldextran chip via the procedure described earlier. This slide shows normalized data in black and the model fit in red. Here we injected each analyte concentration twice, with concentrations ranging from 5 to 0.2 micromolar using a dilution factor of 2. Buffer blanks were also injected and the data was double referenced. That is, both the reference channel and the reference buffer blanks were subtracted out. The equilibrium dissociation constant was found to be 809 nanomolar through the global kinetic analysis of this enzyme inhibitor pair. Since the data shown in the previous slide reaches equilibrium, the equilibrium dissociation constant can be fit from a Langmuir binding isotherm. For each injection, we plot the average response value at equilibrium of about 10 to 20 data points against the concentration. This plot shows that as the concentration keeps doubling from 0.2 micromolar to 5 micromolar, response eventually reaches an equilibrium. The equilibrium dissociation constant agrees quite well with the value calculated previously from the kinetic fit. The next example presents data from an even smaller inhibitor, 95 Dalton methane sulfonamide, binding to the same enzyme, carbonic anhydrase 2. This plot shows duplicate injections of the methane sulfonamide. Again, double reference and fit to a simple bimolecular model to calculate an equilibrium dissociation constant of 652 micromolar. Since equilibrium was achieved, a laminar bind isotherm can also be constructed. This steady-state data yields an equilibrium dissociation constant that is in total agreement with the value calculated from the kinetic run in the previous slide. This gives us great confidence that that value is the correct value. The next example illustrates peptide binding to liposomes. The three steps in this assay are to first immobilize phytosphingosine, second, to prepare the liposome surface, and third, to inject the analyte, in this case a peptide. The following graph shows the amine coupling of phytosphingosine on just the left channel. The surface is first cleaned with 2 molar sodium chloride and 10 millimolar sodium hydroxide. Then EDCNHS is injected, followed by a solution of 0.05 milligrams per mil of phytosphingosine in 50-50 DMSO and sodium acetate, 10 millimolar sodium acetate buffer at pH 5.2. The surface is then blocked with 1 molar ethanolamine at pH 8.5. The advantage of this technique is that when you prepare your own surface, phytosphingosine can be selectively immobilized on only the left channel. Next, we inject the liposomes, again, only over the left channel. This is usually followed by a 50 millimolar sodium hydroxide injection to remove any loosely bound lipid. The following illustration is used to depict what is actually happening on the surface. Note that we use our planar surface, which works much better than a three-dimensional hydrogel for this application. We also have quartz crystal microbalance dissipation data on the same surface to show the presence of water or buffer containing liposomes, indicating that the liposomes are intact. This slide presents data from a phosphorylated and non-phosphorylated peptide binding to the liposome surface. These injections were done using the kinetic titration technique approach, injecting increasing concentrations of the peptide without regenerating the surface. Here we are showing a peptide binding to the liposomes at concentrations of 160, 80, and 40 nanomolar. Note that the non-phosphorylated peptide has a much higher affinity to the liposomes. This technique also lends itself to protein-protein or protein-small molecule experiments. In conclusion, I want to summarize the key features of Reichert and its SR7500 DC system. We saw that Reichert has a proud lineage in designing and manufacturing optical instruments, with well over a decade of experience in SPR instrumentation. Reichert's SPR instruments implement a simple modular design, which minimizes requirements and cost of maintenance, while maximizing the flexibility of the system with the HPLC fluidics and specialized flow cell modules. The consumables are also affordable, which, along with the low maintenance requirements, keeps the running costs of the system very low. The autosampler can accommodate a high volume of samples, up to 768. And lastly, the SR7500 DC has superior performance, which translates into kinetic, affinity, concentration, and thermodynamic data that you can trust. I want to thank you for your time and attention. I am also happy to address any questions and speak with you about your SPR application. My contact information appears on this slide. Thanks again.